today's lesson, we are going to be looking at probability distributions. So in this unit, we are going to add on to the probability concepts that we already know, and we're going to look at basically a new idea, which is basically looking at all of the different possible outcomes, or all the different scenarios, and looking at the probabilities for that. So as a warm-up, for the spinner below, how much would you expect to win every time you spin it? And so take a second to think about how much you would expect to win every time. And some things you may want to think about is, one, the dollar amounts on each of them, because they're not all the same. And you might also think about the size of each panel, or each dollar amount, because those are also not the same. So based off of that, how much would you expect to win every time you spin it? So we will come back to that kind of idea and look at how we might solve, or what we might do to calculate that idea or that expected amount. Before we get into that though, we're going to look at some key terminology that we're going to use throughout this unit. The first is a probability distribution, and this is going to be the main thing that we look at. We're going to look at many different types, or a couple different types, but basically a probability distribution lists the probability of each possible value of the random variable. In other words, we could say that it's a discrete function that describes all of the possibilities of a probability scenario. So if we look back at that example with the spinner, we would basically be making a list of what is the probability of getting 1, what is the probability of $2, $5, $10, and $20, and basically just list all of those probabilities. And then using that, we could use that to help us find some of the expected value. We do talk about, in that definition, the idea of each possible value of a random variable. And the random variable could be one of two things. It could be a discrete variable or a continuous variable. A discrete variable is something that can be obtained by counting, and there are only certain values that the inputs can take, or basically there's only certain values of the outcomes. So for example, if I'm looking at that spinner, there's only set outcomes: $1, $2, $5, $10, $20. Right? Those are fixed. Those are the only inputs that, or the only values that variable could take. I could also look at things like number of siblings, right? You only have 1, 2, 3, 4, 5, and so on, right? They're fixed amounts. There's only certain values that you could have. Now you might think they're going to be primarily whole numbers, which in most cases that's true. However, you could also have scenarios where they're decimals, such as say shoe size, right? You could have a 10 or a 10.5, 11, right? You are allowed those half values, or those decimals, or 0.5 values. However, you can't have anything else. You're not going to have a shoe size that's 12.34, right? So again, there's still only certain values that those inputs or values can be. So say we look at shoe size, number of siblings. You could also say something like number of spins. A continuous variable is obtained by measuring. So again, if it's obtained by measuring, then usually that means there's no limitation on the input value, which means the values that you could be looking at for the scenarios could be anything, right? There could be an infinite number of decimal places, or there are many decimal places. And when we're measuring things, usually that means, depending on how accurate my tool is, I could measure to to many decimal places, right? If I'm using a very accurate stopwatch, or if I'm using a very precise ruler, or things like that can get down to very minuscule measurements, right? So there's no limitation on the input value except for whatever the tool is that I'm using. So these could be things such as, say, weight, right? If you think of weighing something, the weight or the mass that you get is dependent on the scale that you have. The more accurate your scale, the more decimal places that your measurement's going to be. We have weight. You could think of something as, say, height, the height of an object or the height of a person. Again, it depends on how fine or accurate your tool is. You can also think of time. Time's usually a common one, a continuous variable, because again, how accurate your tool is, your stopwatch, your watch, whatever it may be, there's no limitation on what the value you have could be. Now, again, we are going to look at both of these variables throughout the course, but the main one we're going to focus on in this unit is going to be our discrete variables. So we're going to be focusing on only those scenarios or those values where there are, or inputs where there are certain values that you could have. Going back to that spinner warm-up question, how you would solve that is you would look for the expected value, or in other terms, you would look for the weighted average. Because each dollar amount had a different size on the actual spinner, you have to take that into account. Similar how if you're looking at your marks, certain assignments or certain things have a different weighting to it. So you can't just say take the average of all of your assignments and say, well, that's what my final mark's going to be. Some things are worth more, or they have a larger weighting, and you have to take that into account. And that's basically what we're doing here in terms of our weighted average. So the weighted average, what that basically means, or the expected value, it's the predicted average of all possible outcomes. So by using this formula, we are taking into account the idea that some things may be weighted heavier than others. Now this formula may look complicated, but simply put, it is the sum of the products of each outcome, x, with its probability px. So essentially all we're doing is we are taking an outcome multiplied by its probability of occurring and then adding that to each other possible outcome. So just if we need to kind of get some terminology, if we're looking at EX is basically just the expected outcome. This kind of weird looking E is a Greek letter, sigma, that just means sum of. Don't worry too much about the n and the x equals 1. That's just basically saying for n number of outcomes starting at 1. Xn is basically outcome, say 1 or outcome 2, whatever it happens to be. And then the Pxn, is just saying probability of x occurring. Now, if you don't like this formula with all the little subscripts, you could basically just simplify this. So write it below as EX is equal to the sum of x times px. And just understanding that for every outcome, you're going to multiply each one by its probability and then add them all together. So we will look at some of those examples, or we will look at examples of using this first. So example 1, a spinner has two equal sections colored blue, or red and blue. A, make a tree diagram to show the probability distribution for the number of times the spinner lands on blue when it is spun 4 times. So for example, what we're looking at is, if you can't visualize it, we have a spinner with 2 equal parts. One is blue and one is red. And they're equal parts, so we don't have to worry too much about that. So if we're spinning different things, first we could land on blue, land on blue again, or red. Off of the blue, you could land on blue, or spin blue again, or spin a red. The same thing could occur for the other one. So that's 1, 2, 3 spins. Do it once more. Spin on blue, red, blue, red, so that's one scenario looking at blue first. Red would be would be the exact kind of same thing. Spin red first, and we get either blue or red. Basically, it's almost just or it's kind of just the reverse of the last one. So those are the different outcomes that we could have, and now we visualize them. So we kind of wanted to do this because we do want to know how many times, or we want to look at all the different probabilities for when it could land on blue, or looking at the number of times it lands on blue. If we want to double check to make sure we have this, well, we could think, okay, well, how would I figure this out? Well, I have 2 outcomes the first time, multiplied by 2 the second, multiplied by 2 the third, multiplied by 2 on the 4th spin, or 2 to the power of 4, which equals 16. And if I go through and add all these up, each pathway, right, remember we're looking at pathways here, so that's one pathway, or we could look at just the last amount, or kind of the last row, and add all these up, and we would find that we would have 16 total outcomes. So again, we wanted to do the tree diagram because we want to see the specific outcomes, because the next step is going to make a probability histogram for this distribution. And this is basically going to be kind of a very simple version of a probability distribution. So we're looking at, in this case, the number of blue outcomes, or the number of blue or the number of times we land on blue. So there's going to be 5 different scenarios in this case for landing on blue. Either we land on 0, we get 1, 2, 3, or 4 blues, depending on our outcomes. And we can see all these outcomes back up here as well. Let's zoom out a bit. So how many times do we land, or do we only spin 0 blues? And if we go through our scenarios, there's only the one pathway, so it only occurs once. How many times do we land on blue once? Again, if we go through and we look at all of our different outcomes or pathways, we should find that there are 4 ways where we only have 1 blue. How many ways can we get 2 blues? Well, there's 6 of them. Again, going through the same method. 4 blues for 3, 1 blue for 1. Now to find the probability of that, again, we know the total is 16. So what's the probability of getting 0 blues? Well, it's 1 out of 16, which equals 0.0625. What's the probability of getting 1 blue? Well, it's 4 out of 16, which equals 0.25. 2 blues, 6 out of 16, or 3 out of 8. Choose. Keep it as 6 out of 16, 0.375. 3 blues, again 4 out of 16, which we know is 0.25. And 1 blue, or 4 blues, sorry, is 1 out of 16, 0.0625. So this is kind of a simple probability distribution table. Minus the frequency, we're looking at all the different outcomes here, and we're looking at the probability of each outcome. So those two columns represents our probability distribution table. Now we want to make a histogram for this. So we just want to graph this to see what it looks like. It might be a little bit easier. We can kind of see the trends that could happen. So number of times blue will be our x-axis or independent variable. So we'll look at 0, 1, 2, 3, and 4. And for probability, will be on our dependent or our y-axis. And so we'll go up roughly by every 2 is 0.1, 0.2, 0.3, 0.4. And we'll just title this blue spinner or blue spins. So looking at the probability for this then, for 0, it's 0.0625, so just a little bit above halfway. For 1, 2.5. So roughly there. For 2, it's 0.375. So for 2, we're about here. And we can see that it kind of starts to repeat, or it does repeat, exactly on the other side. So then 2.5 for 3. And just a little bit above for 4 options. So that is what our probability distribution histogram looks like for this scenario. So we could look at this and we can say, we can look at what we might expect to happen based on the probabilities and so on. But we might want to be specific about this. So let's go through and let's calculate the expected number of times the spinner lands on blue. So if we look, we'll use our simplified formula EX equals sigma, or the sum of x times the probability of x. So we're going to add up all the different outcomes multiplied by the probability of it occurring. So our first outcome looking at the table is 0. The probability, or we get 0 blues, multiplied by the probability, which is 0.0625. Plus, because it's the sum of, the next outcome. So the next outcome is 1, multiply that probability, which is 0.25, plus the next outcome, which is 2, multiplied by that probability, plus 3 times that probability. Let me just move all this down. Plus the last one, which is 4 times that probability. And then we're going to go through and add them all up. So if we simplify it, 0 times anything is 0, plus 1 times something, which is 0.025, plus 0.75, plus 0.75, plus 0.25, and we get an expected value of 2. So we found that our expected value of 2, and what does that really mean? Or what does that value mean then? Well, what it means is that therefore, on average, the spinner lands on blue 2 times out of 4 spins. So again, it's limited to the scenario that we're looking at, but we found that on average it should land on blue 2 times out of 4 spins, or we're expecting it to land on blue 2 times if I spin it 4 times. We can also use this in a different way. Say, for example, a lottery has $10 million grand prize, a $500,000 second prize, and a 10 $50,000 third prizes. A ticket costs $5 and 4 million tickets were sold. What is the expected value of each ticket? Interpret the results. So what we're going to do is I'm going to create a probability distribution table. So all the different outcomes, and look at the probability of each. So in this case, the variable that I'm looking at is countable because I'm looking at my prizes. And this is going to be my x. And then I'm looking for the probability of x, or each outcome. So if I'm looking at this, I could say, well, what's my first prize? Or the 10 million. So that's my first prize. 500,000 is my second prize. And then I have 50,000 as my third prize. So those are my 3 outcomes. So what's the probability of the first event happening? Well, there's 1 prize out of, or 1 winning ticket, you could say, out of 400,000. Or sorry, not 400,000, 4 million. So 1 prize out of 4 million. For second place, or second prize, there's still only 1 out of 4 million. For third, there are 10 tickets out of 4 million. So those are the probabilities of each. Now we could go through and find those specific percentages if we wanted to, or the specific decimal values, but as long as we're kind of looking through that, then that's good. So why did we figure that out? Well, because we needed to have that in order to find the expected value. Right, again, remember, the expected value in simple terms is the sum of the outcome multiplied by the probability. So that means I need to look at the 3 different outcomes, multiply it by the probability that it could occur, and then add all those outcomes together. So in the first one, we have 10 million, which is outcome number 1, multiplied by the probability that it occurs. So that's 1 out of 4 million. Plus outcome number 2, which is 500,000, multiplied by its probability, which is 1 out of 4 million. And then lastly, plus the third outcome, 50,000, which is multiplied by its probability, which is 10 over 4 million. 4 million. Make sure I got all my zeros there. And when I go through and I add all those up, I get a value of 275, or 2.75. So what does that actually mean? What does this expected amount tell me? And the idea is, I'm expected to win 2.75, or $2.75 with my ticket. That's what I'm expecting to win. So based off of this, so therefore, the average winning ticket value is 2.75, or $2.75. But is there anything else that I can use to interpret, or anything else I can interpret from this answer? So we have the expected value. The other thing that we were told is that a ticket costs $5. So we're told how much it's costing us to play this. So if I take my expected winning, 2.75, and I subtract how much it's going to cost me to play, $5, I get negative $2.25. So I get a second value here that I can use to interpret the results. So because it's costing me $5 to play, and I'm only expected to win 2.75 or $2.75, therefore there is a loss of 2.25, or I'm going to lose $2.25 per ticket. So it doesn't seem likely that I want to play, because it's telling me that every time I buy a ticket, I'm only expected to win $2.75, which means I'm going to lose $2.25 every time I buy a ticket. So again, depending on what information we're given, there could be a couple things that we can use to interpret the results just by finding the expected value. One is how much we're expecting to win, and then two, what is going to be my net result. Am I going to win money overall if I buy a ticket, or am I going to lose money overall? And that's what we can use expected value or the weighted average to help us do. Now, before we go, just one last thing. Today's code word, and today's code word is hush. Again, today's code word is hush. So you can see that from this, we still are incorporating those ideas of probability that we've looked at over the past couple units. Now we're just adding some things to that where we're using it in different ways. We are still going to need to look or remember all the things of probability that we've looked at before as we go through this course, or this unit, sorry. So again, please go back and refresh yourself if you need to.